Good morning, sir. My name is Vamshi. I am from the Triple E department. Today, now I am discussing about a topic of modeling of wind farms in the load flow analysis. Coming to wind farms, wind energy, which is mainly very important in the generation of electricity. Coming to introduction of this wind farm, wind farms are collections of wind turbines that convert wind energy into electrical energy power. The wind energy turbine, which will generate kinetic energy into mechanical energy, and mechanical energy which convert into electrical energy, and is will connected to the grid of the nearby. They are increasingly integrated into power system to enhance renewable energy generation, and this is the renewable energy which is a non-pollution. Understanding their impact on load flow analysis is crucial for grid stability and performance. Coming to in the picture, we can see the wind project of the overview, and the wind turbine, which is a blades which will rotate through the wind pressure, which is connected with kinetic energy to electrical energy to generator, and is which is connected to the substation or nearby grid, and transform to transform distribution lines and the transmission line to substation and to the transformer. And importance of load flow analysis. Load flow analysis is essential for assessing the performance of electrical power system. It is the essential load flow which is very important for the performance of electrical power system. It helps determining the voltage levels, power flows, and losses within the system. Accurate modeling of wind farms is necessary to ensure reliable grid operation. Overview of wind farm components. There are the components which are used in wind energy. Wind farms consist of wind turbines. It consists of turbines and the transformers and the connection and infrastructure. Each component plays a significant role in the overall generation and transmission of power. Understanding these components is vital for accurate low flow modeling. In this picture, we can see the components of the wind turbine, which is placed in a horizontal. There will be two types, horizontal and a vertical. Which is a horizontal, there is a rotor blade which has a three shapes, which has a gearbox and nozzle and generator, power cables, tower, and a transport and a switchyard which is connected to the grid of the substation and the nearby transformers. And there will be types of wind turbine. There are two types of wind turbine. There are mainly primarily two types of wind turbine, that are horizontal axis and a vertical axis wind turbines are there. Each type has distinct character that more influence performance and body. Each type has a different characteristics and a specific further performance of the modeling and a for the turbine plates. The choice of turbine affect the parameter used in low flow analysis. The choice of the turbines, which is horizontal or vertical, which is situated on the situation for the performance of the present particular situation. Here we can see the diagram of horizontal axis wind turbine, and also we can see the vertical axis wind turbine. Yeah, there are already we discussed about horizontal axis wind turbine parts. Here we add a vertical axis wind turbine part, which has it also fixed pitch rotor blade, and there will be a gearbox and a generator. A gearbox used to increase the speed of the turbine blades, which can maintain the constant speed of rotating wind, which can produce constant current power. Wind farms modeling approaches. Several approaches exist for modeling wind farms in load flow analysis. These include aggregated models, detailed turbine models, and dynamic model. The choice of approach depends on the analysis, objects, and system complexity. There are the coming to picture. There are 43 wind turbines in complex terrain. Distance between first rows is level D. Distance between the fourth is 15 D. Aggregated wind farm model. An aggregated model simplifies the representation of multiple turbines as a single unit. This model typically uses the total power output and equivalent impedance. It is useful for large wind farms where detailed modeling is impractical. Detailed wind turbine model. A detailed model represents individual turbines and their unique characteristics. There are different detail model which are constructed in the turbine model, which are different specifications and performs special functions. They different unique functions which are the characteristics. This approaches this approaches captures the dynamics such as turbine control and power curve effects. provides more accurate results but requires more computational resources. Dynamic model of wind farms. Dynamic modeling considers time varying factors such as wind speed and turbine response. In this dynamic, we can see that with rotor which performs in a specific time in a specific minute, how much rounds it will rotates, how much wind pressure is coming, and which it's the wind blades, and how much speed it will rotate, so how much. This model is crucial for understanding system behavior under disturbances. This will measurements which we can use it to avoid any disturbances of this system. It enables better planning for grid stability during wind fluctuation. If there is any wind fluctuation, there will be a better planning to send the grid to power during wind fluctuations. Key parameters in load flow analysis. Important parameters include active power, reactive power, voltage levels, and line impedance. There will be several parameters which are active power and reactive power and the voltage levels and line impedances. Accurate representation of these parameters is crucial for effective analysis. Wind farms characteristics such as power curves and voltage regulation influences these parameters. Power curves Power cuts of wind turbines. Power curves illustrate the relationship between the wind speed and the electrical output. These curves can show the relation between wind speed and the electrical current which is coming output as well. They are essential for predicting the expected generation from wind farms. Incorporating power curves into load flow models enhance accuracy. Reactive power management. Wind farms can provide reactive power support to grid when modeled correctly. Effective reactive power management improves voltage stability and reduces losses. Understanding turbine capabilities is essential for accurate reactive power representation. Integration of wind farms in load flow studies. Integrating wind farms into load flow studies requires careful consideration of a grid connection. The impact of wind variability on power flows must be assessed. Models must account for both steady state and dynamic condition. Here we can say it is a renewable energy generation integration into grid. There will be in the picture, there will be seen that there will be residential and commercial distributed generation which has approximately 5 to 500 kilowatt and generated behind the meter. Community scale distributed generation approximately 500 kilowatts to 5 megawatts enters the grid view distribution lines. Centralized utility scale generation approximately 20 plus megawatts power entire grid as a transmission lines and is distributed to the customers. Challenges in wind farms modeling. One major challenge is the variability and unpredictability of wind resources. Another issue is the interaction between wind farms and conventional generation sources. Addressing these challenges is crucial for reliable load flow analysis. Power production of wind turbine will be a circle which can form a single power production of single and wind turbine which can calculate with the PWT equal to 1 by 2 Cp dm by dt v square equal to 1 by 2 Cp VAV cube. Cp is nothing but power coefficient. Case studies for wind farm integration. Various case studies illustrate successful integration of wind farms into existing grids. These studies provide insights into best practices and lessons learned. Analyzing real-world examples helps define modeling techniques and approaches. Software tools for load flow analysis. Several software tools are available for conducting load flow analysis with wind farms. These tools vary in complexity and features catering to different user needs. Familiarity with these tools is essential for effective modeling. Future trends in wind farm modeling. There will be advances in technology leading to more sophisticated modeling techniques. Machine learning and artificial intelligence may enhance predictive capability. Studying ahead of trends is vital for accurate and efficiency of load flow analysis. Here we can see the power system value barriers onshore wind turbine, which has the offshore and onshore. Wind speed 7.5 mm, specific power to 21 we can see, and the wind speed 9.5 mm and the fan size 500 to 9699 megawatts. Catex which will be future trends. Regulatory and policy consideration. Regulations and policy influence the integration and wind farms. Integrity comprehensive standards is the essential for operational efficiency and safety. Understanding these considerations is key to successful modeling and integration. Environmental impact of wind farms. Modeling also encompasses the environmental implications of wind farm integration. Assessing these impacts helps in gaining public acceptance and regulatory approval. A comprehensive approach includes both technical and environmental factors. Coming to conclusion, accurate modeling of wind farms is essential for effective load flow analysis. It requires a multifaceted approach considering various technical, regulatory, and environmental factors. Continued research and development will enhance our ability to integrate renewable into power system. Here will be some of the renewable energy CA simulation inspection solutions, which are blade dynamics, wind farm aerodynamics, composite materials, wind turbine blade, wind turbine blade, and aero accuracy. Thank you.